Last time we finished proving the Sylow theorems, and I gave you the following corollary. This kind of gives us a sort of a snapshot of an important thing that can occur with Sylow subgroup. Suppose that you have a P being a Sylow P subgroup. So that is a subgroup if the order of G is P to the A power times M, where M has no more factors of P in it, then a P Sylow subgroup is a maximal P subgroup. That is order P to the A. The following conditions are equivalent. These are all equivalent conditions. Number one, P is the only Sylow P subgroup, so there's only one of them. That means that P is normal in G, and conversely. That means P is characteristic in G. And finally, it means that if you have any subgroup of G generated by elements of order P to the K, so you just generate it by these elements of prime power order, then that forms some P subgroup. Okay. Let me just kind of give you a brief why is this true. If there's only one Sylow P subgroup, then when you conjugate it, it has to go to another P Sylow subgroup. There's only one of them. That means that any conjugate of P has to be P. So P is normal G. We know that characteristic implies normal from homework. Why is the other case true? Well, if P is normal G, suppose you have any automorphism of G, right? What does it mean to be a characteristic? It means when you take an automorphism on this, it's still inside here. But take an automorphism of your P Sylow subgroup, right? It actually has to be in P because of the normality, and because the image of any group of order P to the A is still P to the A, it's also characteristic. On the other hand, what's this all about? Well, if there's only one Sylow P subgroup, then every element of order P to the K is in there. So any subgroup generated by elements of this form must be inside this P. So it's again a P subgroup. That's basically some of the high points of this in broad strokes. Let me give you another application of this. Here's another application. Show number of order 36 is simple. Somebody want to remind me what it means for a group to be simple? Do I remember this? Yes.
Is it the only normal subgroups are the entire group?
That's right. It's got no non-trivial normal subgroups is what it means to be simple, right? So let's take this apart. We did a problem like this before where all we had to do was kind of count the elements. This one's got a little bit more teeth to it, right? There's a little bit more oomph to this one. And let's take a look at this. The order of G is 36, 2 squared times 13. So there's only Sylow 2 and Sylow 3 subgroups. Those are the only primes dividing. Okay, for the number of Sylow 2 subgroups, the Sylow theorems tell us that N2 has to be equivalent to 1 mod 2. All that means is it's odd. And N2 divides 9, so possibilities. Okay, big list there. All right. N3 and N3 divides 4. Well, the divisors of 4 are 1, 2, and 4. Which one of these are equivalent to 1 mod 3? Well, only 1 and 4. Everybody agree with that? Well, at least in this case, we've only got two suspects instead of three, right? Okay. If G is simple, an entry of simple, right? That means it's got no non-trivial normal subgroups. What happens if N3 is 1? If there's only one Sylow 3 group, that means that Sylow 3 group, which is of order 9, is normal in G, right? And if G is simple, that's not possible. Everybody agree with that? So the choice N3-1 would mean that G is not simple because it's got the 3 group, Sylow 3 group normal. But we got one choice left. Everybody okay with that? Yes.
Could you go over that again in a bit more detail?
If N3 is 1, that means there is a unique Sylow 3 subgroup, which means that that Sylow subgroup is normal. So now you've got a subgroup of order 9, the Sylow 3 group, that's normal in G. And that contradicts our assumption that it's simple. That makes sense?
We don't be assuming that it's simple because we're doing it for contradiction.
Right. Assume that we do have a simple group, and we're going to run into a brick wall here in a bit. Assume that G is simple. Well, that means that you have to have 4. Now, you know, I really would like to count the elements, but this is very complicated. Suppose I've got 4 Sylow 3 subgroups. They all have order 9. I don't even know what these groups look like, right? In fact, what do I know about a group of order 9? Well, I know it's a billion because it's p squared, but beyond that, I don't know much, right? I don't know what the conjugates look like. These groups could be cyclic of order 9. They could be Z3 cross Z3. They could intersect at subgroups of order 3, or they could intersect trivially. These are all kind of different things that could happen. It's hard to count the subgroups, even if I know that there's exactly 4 of them. It's easiest to count if they were of order 3, I can count some elements, but they're not. They're of order 9, which is more complicated. Okay. So here's a neat trick on group actions, which is, I mean, how do we, 4 is a small number, would everybody agree? Too big. So we're going to take some of this business we have with group actions, which is to our thing. Let A be the set P1, P2, P3, 4 of our Sylow 3 subgroups. Right? We've got 4 of them. Right? Let G act on the set conjugation. So what I mean by this is G acting on one of these PIs is G, PI, G inverse. Right. So I can let G act on the set of 4. Remember, they're all conjugate, right? That's one of the Sylow theorems. And so we just let G act on this. G acts on P1 by conjugate maybe to P3. Maybe it conjugates it to itself. I don't know. The different G's. For example, the identity, we'll just leave all of these alone. It won't permute at all. But other elements might take P1 to P3 and P2 to P4. Things like this, right? This is a group action. And what do we have? Well, this gives a homomorphism. I'll call it phi from G into S4. Right? Because every one of these G's gives you a permutation of the set A. Right? In fact, I will write this permutations of A, which is S4. Every one of these G's corresponds to a permutation of these four things. This was our big group action theorem. It says when you have a group action, it gives rise to a homomorphism from the group until the permutations of the set you're acting on. Right? Everybody remember that? In this case, you're acting on four things, four Sylow, three subgroups. So that gives me a permutation from G, or this conjugation action gives me a homomorphism from G and S4. Everybody with me so far? Now, let's think about this homomorphism. What is the order of G? It's 36. What is the order of S4? Right? And I don't know much, but I do know that 36 is bigger than 24. I agree with it. So what can I conclude from this? The kernel of phi is not equal to the identity of G. Why is that?
There are some things in G that must be to repeat things in S4.
That's right. If the kernel of phi was the identity, that would mean that this is a one-to-one homomorphism, right? Well, there's not even a one-to-one map of sets because 36 is bigger than 24. You can't even do it for sets. So I think that we can conclude that the kernel of phi is not the identity. Let me also conclude that the kernel of phi is not identity.
Not the identity?
Okay, yes, thank you. Not the identity. Also, kernel of phi, and I'll get it right this time, is not equal to G. Why is that? What happens if the kernel of phi is G?
There's no possible way for it to lead to all 24 elements possible.
There you go. That's essentially the gist of it. If so, then G acts trivially on, that is, G acting on PI for all I, for all G and G. So if the kernel is everything, that means that every one of these permutations is the identity permutation, right? And that means that every one of these is left alone by conjugation. Yes.
So that would mean that they're normal.
And that would mean they're
That's
normal,
not possible.
and that's not possible. This would imply that each PI is normal in G, which is a contradiction. That's a very good way of looking at that. Another way is what the Sylow theorems say, that all the P-Sylow subgroups are conjugate, right? So part of what the Sylow theorem says is pick any two of these, P1 and P3, there's something that conjugates this to this. They're all conjugate, right? And that's another way to look at it. I think I like your observation better, right? It would imply that they're all normal, and they can't be because they're not unique, right? Good. So, per phi in G is not the identity of G or G. And ker phi is always normal in G. So G is not simple. Yes.
Contradiction, 2 lines up from where you ended, is that coming from just properties of the Sylow subgroups? Or is it
That's
coming
right.
from,
So what we have here is 4 Sylow subgroups, right?
they can't be sent to anything else?
If
But
there-
if
if
that
there's more than one
existed,
Sylow subgroup, they can't be normal.
that's
Yeah,
not-
there's lots of ways to kind of skin this cat as far.
That's not based on our assumption that this is simple, right?
Yeah, that's right. We get down here and finish it off. Okay. Any other questions on? This is, yes, go ahead.
So kernel of phi, we know that that's always a subgroup of G, and we know that it's not E or G. And we always know that kernel of phi is normal.
It's always
How-
normal.
So how does that mean again that it's not simple?
Because what you have is a normal subgroup that's not the whole thing and it's not the identity. Others? All right. Okay, this is kind of another, thing for your trick bag. If it's hard to count the elements, sometimes this kind of counting the Sylow subgroups and, looking at, a conjugation action sometimes helps as well. Yes,
Actually, no, I think I'm okay.
you okay?
Yeah.
Okay. Okay, see if you can use the Sylow theorems to find all groups of order 12, just for fun. That's, you can kind of start picking out some orders. Let me give you kind of another, just for fun, kind of a challenge problem that's, okay, so here's a fun problem. If you look at all groups less than, well, let's say less than 100. You've got a bunch of simple ones. They're all prime order, Z mod 2, Z mod 5. They're all the abelian simple groups. I consider them the simplest of the simple groups because they're abelian. Their only subgroups are themselves and the identity. Let's ignore those because they're kind of silly. Anybody know an example of a simple group of order less than 100? There aren't a lot of alternatives here. That's right. The alternating group on 5 elements. A5 is of order 60. That is a simple group for less than 100. That is the only one of order less than 100 that's not abelian. So just for fun, see if you can pick out the numbers between 1 and 100 and show that there aren't any, except for 60, there aren't any ones that are simple. The hardest number, in my opinion, to prove, it's rather involved, is 90. So you can give yourself a little diamond shaped crown or something if you can do 90. So that's kind of the big challenge. Okay, so any questions on that? All right. So that's the Sylow theorems, some of their applications. We use a little bit here, but we are actually going to look at a class of groups now that are probably a little bit easier to handle. We're going to talk about the general construction. We're going to talk about direct products, semi-direct products, which you've gotten a little bit of an introduction to in your homework, but we're going to do something more extensive. And then we're actually going to go through the process of classifying all finitely generated abelian groups. So in particular, finite abelian groups, we'll be able to list all of them, which is really kind of cool. So that's a nice end result. So in the family of groups, if they're finite and abelian, then I can tell you in a certain sense what they look like. Foldables. Semi direct products. and finitely generated. Okay, so let's first talk about semi-direct products. Definition. Let's suppose that we have a family of abelian groups. Suppose I have a family of groups. Then the product, so if you take the Cartesian product of GI, and this could even be over an infinite set, but if the set's finite, you could just think of this as like Rn, right, in a certain sense. So you've got like a finite number of coordinates that you fill. This is the set of, I'm going to write this from my product notation. So each coordinate, the first coordinate has an entry from G1, the second from G2, et cetera, et cetera. Okay, so I'm going to tell you how to put these things together. A prime. Suppose I have one generalized sequence, one thing in the Cartesian product here, another thing in the product here. How do I put them together? Well, each one of these things is a group separately. We do it like this. So the familiar, this is a generalization of what you saw in the homework. Here's something like kind of a familiar example to kind of go with this. So this just generalizes this. Instead of just writing an ordered pair and keep on the H, I write this sort of as a potentially infinite ordered, infinite tuple, perhaps. And the way I combine these is just multiply them coordinate wise. Just following the rules. G comes from a group, H comes from another group, and we're just going to follow the rules this way. This is a group. You proved this for the 2 case in your homework. Let me make a couple of remarks. If G1, G2 up to Gn are finite groups, actually don't even really need finite here, but it's most meaningful if I do that, then this isn't really a group theory thing. This is just a set theory thing. This is just a counting thing. So the number of elements in this generalized Cartesian product is just the number of choices for G1 times the number of choices for G2 all the way up to Gn. Okay, so got that going for us. if A and B are abelian, and in some contract, A direct sum B instead of the direct product. Now, more generally, there is a distinction between the direct product and the direct sum that I will make clear here. Definition. So, but GI, a family of, I'm going to put this in parentheses, explain what I mean here, groups. Then the direct sum of GI opposed to the direct product is a subgroup of the direct product. And what's the subset? Direct sum where GI is the identity of GI for all but finitely many. Okay, so let me clarify what's going on here. What's the distinction here? Let me take a simple example here. If I look at the direct product of Z2, you might think of a typical element of this has infinitely many coordinates, right? And all those coordinates consist of either 0 bar or 1 bar. Everybody agree? I've got complete freedom, right? The direct sum of Z2 where epsilon I is 0 bar for all, but at most finitely many entries. So I've got this strange restriction here because almost all of this has to be zeros. I can only have finitely many non-zero entries. So for example, 1 bar, well, 0 bar, 0 bar, 0 bar, 0 bar forever is in both. It's in here, it's in here. And in fact, it is the identity of both. 1 bar, 0 bar, 0 bar, 0 bar, 1 bar, 0 bar, 0 bar. All of these are in forever and ever are in both. However, if I look at one bar, one bar, one bar, one bar forever, this is in the direct product of Z2, not direct sums of the two. Anything that is in the direct sum of Z2 has to end in an infinite string of zeros. Because after a while, you've used up your finite many and you have to end in an infinite string of zeros, right? This also, one bar, zero bar, one bar, zero bar, one bar, zero bar is in product, not sum. If this pattern is continued. Right? Does everybody see the distinction? The direct sum has to end in an infinite string of zeros. The direct product doesn't. You've got complete freedom. Let me point out, for those of you interested in such things, this is generally much, much, much bigger. In the sense that this, would you agree that this is an infinite group? This is infinite too. It's countable. This one is uncountable. It's much, much bigger, as a matter of fact. But that's the direct product and the direct sum. Yes.
I'm still a little bit confused on what's after the such that the direct sum.
Such that. It means that the entries of this have to be zero for every entry except finitely many, right? So here's the problem. This one right here, this one right here, they have infinitely many non-zero entries, right? Entries that are on the identity. So they're not in the direct sum, right? So your direct sum has to have only finitely many things deviating from the identity, right? How many of you think this sounds totally wacky made up crap? Right? I mean, this makes more sense to me, right? I mean, just complete freedom, right? We're Americans. We like freedom. So direct product, we can put everything in there, right? The direct sum seems kind of made up. I mean, why would we do this? Because it's only got, why would we even do this? Actually, it's extremely important. In a certain sense, the direct sum is more important than the direct product, at least from my research perspective. It turns out that you can realize the direct sum, direct product is a homomorphic image of the direct sum. It just has to be over a bigger set. This is not made up. There are actually kind of deeper reasons for this time. Why this makes sense and why we define it this way. It's not just for creating homework problems. And we'll see why that's the case as we go along. Let me give you a theorem now that I'm going to give you only for the finite case, but it can be extended in a natural fashion to the infinite case. And if you want to get under the hood with me with that, then that's great. We can talk about that later. I'm more restricted to the finite case just for the sake of exposition and also because that's where we're going to apply it pretty soon. So let me get the following. Theorem 715. Suppose that we have groups G1, G2, Gn be groups. And suppose that G is their direct product. By the way, let me point out something that I should have pointed out a little before. The direct sum means that you can only have finitely many non-identity entries, right? So if you have a finite direct product, there's no distinction with the direct sum here, right? So all the entries here, if this were a direct sum, you've got complete freedom because there's only finitely many entries in the first place. Number one, for all I between 1 and n, GI is isomorphic to, I want to give you a little subgroup of this. This is the subgroup of the direct product where you fill everything up with the identities except for the I coordinate. That little piece of that direct product is isomorphic, as you might guess, to GI. Additionally, the image of GI define iota sub I from GI into G1 cross GI cross GN via I'm going to define this map in the way that I think is kind of easiest. This is called the inclusion map. What I do is I take GI and I shove it in the GI coordinate correctly, and I fill everything else with identities. This is a homomorphism. The image of iota sub I is isomorphic to GI, and comma, the image of iota sub I is normal in G, the direct product. And anybody want to guess what this is? If you take G mod I want to guess what this is. Isomorphic to. Let me write this explicitly. This is G1 cross G2 cross GI cross GN modulo image of iota sub I. Anybody want to guess?
Is it anything that only has identities or never has an identity?
This is isomorphic to 1 cross G2 cross GI minus 1 G plus 1. Notice when you quotient out, the image of this looks just like it's the piece of GI that's inside of here. And what you're doing essentially when you quotient out is you're killing that. So notice how in this direct product, you're missing the GI part, right? Also, I'm going to give you kind of a similar map here. Too, for all I between 1 and n, we have this, what's called a projective map. We define pi to be the GI. Okay, so that's the easiest way that I can take an element of G, which is this ordered n tuple, and return something in GI. What's the laziest thing you can think to do? Yeah, just read that ordered n tuple and pick out the appropriate coordinate. You know what? GI. Goes from here. This is an onto group homomorphism. And the kernel pi I. Anybody want to tell me what the kernel is? Well, let's see so what does it take to be in the kernel? What lives here has to be one. Everybody agree with that? But as long as this is one, anything else over here can be anything you want. So it's actually G1 cross G2 cross GI minus 1 cross GI plus 1. Similar in theme to this, right? Yes.
Going back to that, we have a function iota that can be fed any GI, and it returns a set similar to that, or a collection of sets
Right.
similar to this.
For every one of these i's, G1, G2, there's an iota 1 for G1, an iota 2 for G2, an iota 3, and so
So
forth.
the
So on.
image of that function, wouldn't that be any set of that form where you have a bunch of stuff and then that GI somewhere in the center?
No, because what I'm doing here is the way this function works on an element is I need the identity in all these coordinates. And then this is where the variable tells me to go in the ith coordinate. So it's ones everywhere else. I need this for this to be a homomorphism. And I think we'll see that proof actually.
Why isn't the image still a collection of?
Well, the image as a set looks like this. As a set, looks like 1G1, 1G2, 1GI minus 1, GI, 1GI plus 1, to 1G.
So when we take that and we've removed all that from the product of all the sets, why aren't we then removing any possible GI? Because that GI could be in any position depending on what I were inputting into the function.
No, so once I've fixed this, I've fixed the coordinate where it's going, right? Once I've fixed that I, right? That's what I mean by there's an iota 1 in the first coordinate, there's an iota 2 that takes G2 to the second coordinate. This is fixed into the ith coordinate. And that's why I have to keep the identity here. And as a set, the image looks like this. So it's basically everything that's got all identities, and then you can vary this however you want. And that's why it's isomorphic to that.
So the I is fixed, and from that we can feed it anything in that specific GI.
Yeah, that's right. And it's going into that specific ith coordinate. So notice that G mod kernel I is isomorphic to GI. That's the first isomorphism theorem. And finally, 3, if I is not equal to J, then iota I of GI times iota J of GJ is iota J GJ iota I GI. So if you have two elements, basically what that says is two elements of different coordinates sort of commute with each other. Okay. We're going to talk about the proof of this later, but let me make an observation here. Let me look at some simple direct products. Notice anybody see how to break that up as a direct product? I'm going to write this as a direct sum because these are abelian groups. We're going to go over it later. In the same fashion, Z4 cannot be decomposed like this. Anybody know, can anybody guess what the kind of the difference is about these numbers, 6, 15, and 4? What makes 4 different? Why can't I break that down, say as Z2 cross Z2?
So, prime square.
That is correct. Notice that the pieces that we broke Z6 up into are relatively prime. Z15, 3, and 5, they're relatively prime. That is, the GCD is 1. We're going to pick this apart later, but let me give you a theorem to wrap it up for the day. Let me see quickly why this is true, and we'll see that this applies to this case here. Example, so let theorem. So, let H and K in G be subgroups such that 1, H and K are normal in G. So suppose they're both normal, and suppose that the intersection is the identity. Then G is the direct product. Let me show you how this works for this case here. I'll let you guys do the other one. Let me do Z6 here. Let me give you two subgroups. These two subgroups are normal in Z6. Somebody quickly tell me why. What's true about Z6? It's abelian. So all subgroups are normal. These are two subgroups. It's clear the intersection is the identity, right? Because 0 is the only thing in the intersection. Agreed? And oh, there's another condition I need. That's what I meant to write. The product group is the direct product here. And that's what happens here is the product group is the direct product. Now, in this case, we get lucky because the product group generates everything. Because notice, what's 3 bar plus 4 bar? 1 bar. So if you have these two groups put together, you get everything. You got the identity. We'll talk more about this next time. Any questions? All right, I will see you folks on Wednesday. That's it for today.